Welcome back to day 5 of Organometallics. Quick administrative reminder, your Wikipedia topic selection is due in 2 days on Thursday. Thanks for those who have already emailed me or already emailed the TAs. I recommend, if you haven't thought about it yet, start thinking about it. And you know, we're always, as a teaching team, we're always happy to help you refine an idea. If you maybe have some general thoughts about something that you're interested in, then let us know and we can help you refine that and direct you to existing articles. But we can't do that if you don't get in touch. So please be proactive there. Okay, in terms of just a quick overview of today's topics, we'll very briefly wrap up what we concluded the last lecture with, which was discussing ligand exchange mechanisms and reactivity trends. Then we'll move into the, I guess, the meat and potatoes of today's lecture, which is discussion of oxidative addition and reductive elimination, which, as you'll see, are two sides of the same coin. And then time allowing, we'll conclude with a couple quick hitters on 1,1 migratory insertion, but the bulk of today's talk will focus on oxidative addition and reductive elimination. Let me okay, how is my screen share working? Okay, looks good, thank you. I have a tendency to, like, over time write smaller and smaller. My default writing is very, very small. So if there's ever things you can't see, then just put it in the chat window. I can zoom in. So probably like by the end of the class, you just see like small dots going across the screen. So just as a quick review, we talked about ligand substitution mechanisms, the commonly observed pathways, associative, dissociative. We talked about the kinetic profiles of these two processes and then different ways to encourage ligand exchange. So we'll start out today's talk today's lecture by focusing on the underlying kinetic trends of ligand substitution and also underlying selectivity, or the kinetic principles that underlie selectivity trends. And we'll start out by discussing the trans effect or the trans influence. So a quick bit of nomenclature. The trans effect, if strictly speaking, you know, people in the literature sometimes get a little bit lazy and use these terms interchangeably, but strictly speaking, the trans effect should be reserved to a kinetic phenomenon. So selectivity for substitution at one position versus other position. The trans influence should be reserved for describing a thermodynamic phenomenon, for example, bond lengthening or bond weakening as observed in X-ray crystal structure or in IR stretching frequency. The trans effect is most important for D8 square planar complexes. It also it plays a role in octahedral complexes, but I think in D8 square planar, it really plays a dominant role. So that's what's often used for discussing specific examples. And in terms of just a definition, this is an empirical phenomenon that certain ligands are found to be more effective than others in labelizing a ligand that are a ligand trans from itself. So I've tried to depict that here. I'm trying to get like creative with my use of color. So the ligand in question, the trans influencing ligand here, is the one highlighted in pink, and the ligand that's being exchanged is the one that is denoted X, and I'm using these exchange arrows. And so the underlying, so this is an empirical trend. This doesn't like fall out necessarily of first principles, but the rationalization of this trend is that ligands that have a strong influence are those that in a associative pathway, which again is most common for D8 square planar, the reactions are proposed to proceed through a trigonal bipyramidal intermediate. The incoming and outgoing ligand and this trans-influencing ligand all lie on the same equatorial plane, owing to the principle of microscopic reversibility. And ligands that have a strong trans-influence are those that are typically strong pi acceptors, or that don't have lone pairs to donate as pi donors, because the equator of a trigonal bipyramidal, the d orbitals involved tend to be more pi basic. So you want ligands that can counteract that effect. And then the outgoing ligand leaves, as I said, via the microscopic reverse of this association process. So I went through that quickly. If you're curious about it, I'm happy to go into more depth, or you can read about it. Here is what the empirical trend looks like here, highlighted in blue. Let me. And one of the points I want to make is that I think is a little bit not obvious in some organometallic classes. This is just glossed over, but because this is an empirical trend, the exact trend, the exact order that you would get depends on the experimental setup, and namely the metal and the complex that is used as a starting material to run the experiment. So if you ever encounter a list where the order is slightly different than this, I think in general the trends hold, but the particular ordering might be a little different. It's probably because they use a different metal and a different starting material complex to collect this data. The data shown here is the one from the Hartwig textbook, and the original reference is shown on the right, this Cord Chem review. In general, things that are strong pi acceptors have a strong trans influence, and then alkyl and silyl hydride ligands also have a very strong influence. On the flip side of that, things that tend to be more pi donating ligands tend to have a weak trans effect. Okay, so let's go through one specific example. And so this would, for anybody who has taken an organometallics class or done a boot camp, this will probably look familiar. So if one considers this tetrachloroplatinate starting material, and then treatment with an equivalent first of ammonia, here there's no, okay, let me see if I can be creative and use this copy paste tool. So in the first step, there's no, all four ligands around platinum are equivalent. So all that's going to happen, that's not right, is that you exchange one of them. There's no selectivity considerations here. I can even try to use the same coloring system to make this as clear as possible. Although by the time I'm done with this, you'll probably have already finished. Okay, and then taking this one step further, actually I shouldn't color this one in, this will confuse you. So now we get loss of another chloride ligand. Now the complex is neutral. Okay, and now you have, the key point here is that you have two potential sites of substitution that are inequivalent. You have one that is cis to the ammonia, and one that is trans to the ammonia. And I'll just ask for a volunteer here. Omar, which of these get substituted based on what we just covered?
The orange chloride.
Okay. And the name of the product is?
Cisplatin.
Cisplatin. Okay, great. This is like, I think, the archetypal example of the trans effect. So you feel like, as an instructor, if you don't cover it, they're going to revoke your license to teach or something. So the key point here is that now you had the quick comparison that Omar did is basically comparing the trans influence of the ammonia with the trans influence of the chloride, and you just consult the list and you see that the chloride has a stronger trans influence than ammonia, and so that is the ligand that gets exchanged. Is that right, Omar? Oops. Sorry, I'm trying to just use the same coloring scheme as above, so this looks as clear as possible.
Hey, Gary.
Yeah.
Would this be an example of the trans influence or the trans effect?
This should be an example of the trans effect. Sorry if I said trans influence. See, I told you people use this, I get sloppy and use this interchangeably. So trans effect, thanks.
Okay, thanks.
And then in terms of trans influence, what you'd expect to see is, let's say you took a crystal structure of this intermediate, you'd expect to see the chloride that's going to be exchanged having a longer bond length. Okay, and then another effect that is, so I think in general, there's a lot of focus on the trans effect, but the ligands trans to ligand being exchanged are not the only thing that affect this overall coordination environment and the electronic structure. Also, the ligands cis have an influence, and so there's another effect called the cis effect, which I think tends to be more important for octahedral complexes and square planar complexes. And so here, it's just the basic crux of it is to think about a dissociative pathway, and then from this dissociated putative intermediate, think about what would be stabilizing and what would be destabilizing. So this sort of intermediate, so now we're talking about with respect to ligand X. So things that could that would be stabilizing would be those that can be bidentate or have the ability to toggle between monodentate and bidentate. It would be destabilized by things that are strongly sigma donating X. And then if we think about the effect that this same ligand would have on labelizing the ligand trans to it, this is going to be destabilized by strong pi accepting. So of course, like what ligand gets exchanged is always a competition between cis and trans. So you have to not only consider the things that stabilize what would be the cis pathway, but also things that are destabilizing to what would be the trans pathway. And then the order is shown here. I think, and as sort of a very first rough approximation, you could say that this tends to be opposite of the trans effect, with the exception of these ligands that can be stabilizing through bidentate coordination, which have an added wrinkle to them. That's not precisely true, but first approximation. Okay, so let's now conclude this section by wrapping up our problem of the day from day 4 and the last problem on the worksheet. Is everyone able to see that from my screen if you don't have it? Nobody's able to see it? How about now? Okay. Yeah, there's no like thumbs down reaction emoji, is there? There's only approval ones. So, okay, yeah, thanks for everybody who's giving me the thumbs up, thumbs down. Okay, so this asks you to consider a penta carbonyl manganese halide complex, or rather a series of those with treatment upon treatment with triphenyl arsenide, and asks you to predict the product and propose a mechanism based on the things we've discussed. I think that should be pretty straightforward. And then part B asks us to order the 3 complexes in terms of expected reaction rate. So I'll give you 30 seconds to think about that, and then I'll call on a volunteer. While you're thinking about it, I'll just jot up the reference for this. If anybody's quick enough to pull this up, then more power to you. Okay, Noor, are you there?
Yep.
So what would you expect the product here to be? Or products?
Well, I guess looking at it's going to be a substitution.
Yep.
The obvious part. So it's an 18 electron complex. So it should be a dissociative mechanism. So the halide should depart first, and then the arsenide, I think, should coordinate, well, should essentially bind to the manganese. Since you have essentially all ligands are the same and they're all strong pi acceptors, I mean, it wouldn't really matter where it lands, I think, because it would all be equivalent.
Let me go back to my screen. So I think the key question here in this first part is what ligand is going to depart. I think you correctly recognized the 18 electron. It's got to be dissociative mechanism. Some ligand's going to be exchanged. Is it going to be the halide or the carbonyl? What's a potential complication with the halide exchange?
Potential complication.
Well, the outgoing halide is an X-type ligand, and the incoming ligand
Right.
is an L-type ligand. So that would make the product you propose to be what?
Well, the incoming ligand would be an L-type, so that would be neutral. So the overall complex should be positively charged.
So it makes the complex cationic, which would be destabilizing.
I see.
And you also have, remember, this balance with 5 ligands, all carbonyls, all quite strong pi acceptors. Probably, if anything, this is a metal that wants to get more electron rich on the net.
Yeah, I guess something that I think of is usually neutral ligands depart faster than anionic ligands, but in this case, I'm thinking of the pi accepting abilities of those. So it makes me wonder the strength, the bond strength of the carbonyl versus the halide.
Okay, let's draw the starting material. Okay, so Noor's first instinct was to exchange the halide, and then we talked a bit, you know, the alternative is carbonyl, and then in this case, you have two potential carbonyls. If you exchange the X, there's no selectivity issue, and since the question came right after the cis and trans effect, probably a cueing that there should be some selectivity issue to consider. So let's consider these two potential outgoing ligands, Noor. So which of these two inequivalent carbonyls would you expect to depart if you had to pick one?
The one on the equatorial site.
Okay, and why is that?
Because it's trans to a strong pi acceptor.
And I can sometimes really make a mess of these pen tools. Okay. Okay, good. Are we aligned on part A? And how about part?
Carrie, can I ask you a question? Is it just
Yes.
one of the phenyl ligands being exchanged, or is it the arsenic itself coordinating to the manganese?
Sorry. I forgot that this was a arsenide ligand. Is this what you're asking about, Kelly?
Yeah, thank you.
I just misdrew that, sorry. So try triphenyl arsenide and triphenyl phosphine these are like isostructural and isoelectronic ligands. So just in my mind, I saw one and thought the other. Okay, and so now part B, Noor, what do you think of those three complexes, iodide, bromide, and chloride? Which would you expect to just, you know, you don't have to put any hard numbers on this, but what would you expect the relative rates to be? Or what order, let's say?
So I guess based on what you've explained in the previous section, that if the ligand cis to that to the departing ligand would be destabilized by strongly sigma donors. So I guess maybe I would think of the relative sigma donating abilities of the halides.
Okay, so what would be the fastest?
I think the fastest would be the iodide.
Okay. Did anybody get anything? What, did anybody get I guess the opposite trend? So in this case, Noor, remember that there's, you know, like the, so this is one of these cases that the trans ligand is held constant across the series. So the only factor that's going to be at play is the cis ligand and the cis effect. If we go to our handy dandy empirical list, we see that chloride has a stronger cis effect than bromide than does iodide. And so there's about a one order of magnitude difference between these. Three, and these are all in units of per second.
Sorry, I have a question.
Sure.
So I didn't really understand why the cis effect, the ligand will be destabilized by the sigma donating of X.
Oh, so you're asking about this second bullet point?
Yeah.
Yeah, I think it has to do with the fact that let me see what I mean, I think one kind of quick and dirty explanation would just be that you have things that are more strongly sigma donating are going to make the push electron density onto the metal, and they will destabilize the metal ligand bonds most proximal to them.
Okay, thank you.
Yeah. Okay, super. Any additional questions on that? Okay, let's press forward then to conclude this section with just a bit, or rather to transition now with just a bit of nomenclature. So up until this point, we've covered ligand exchange reactions. So these are reactions where the organic fragment or the ligands involved do not really undergo any fundamental change. They're bonding to the metal, they're dissociating from the metal. But for organic chemists, I think always our interest is reactions that actually can modify the ligand when it's on the metal. And so that's what we're transitioning to now with oxidative addition, reductive elimination. Quick bit of terminology. So ligands, as you will see in this lecture and then throughout subsequent lectures, can kind of play two roles during the course of a reaction sequence or a catalytic cycle, which is some subset of ligands stay on the metal and they modulate reactivity, but they themselves do not get modified at any point. And we would call those spectator ligands, or in the literature, you also see the terminology ancillary ligands. And then the other type are those that are involved in bond making and bond breaking, and those we would call actor ligands or reactive ligands. And so just one quick example from the area of alkyne trimerization chemistry. So an active alkyne trimerization catalyst is this ruthenium, CP ruthenium chloride bisphosphine. Sorry, let me get to the right page on my notes. So the CP ligand is bound to the metal during the whole reaction coordinate. So it's of course affecting the electronic properties of the metal, but it's not involved in the business end of the transformation. So we would call that a spectator ligand. The phosphines and certainly then the alkynes that are involved are actor ligands. And we will come back to this if the mechanistic details are foggy at this point. Then don't fret. Okay, let's jump in now to oxidative addition. This is a process where, if you like arrow pushing, 2 electrons from a filled d orbital on the metal get pushed onto the organic fragment, the organic ligand, leading to cleavage of, in this case, just the generically represented AB bond. So we talked about pi back bonding. I like to think of oxidative addition as like pi back bonding taken to the extremes. When pi back bonding to from the metal to the ligand is so intense that it actually ruptures the bond involved. So this is the generic depiction, just in terms of some kind of defining the definition and sort of key features. There are two sort of flavors that we'll cover. So oxidative addition will break a sigma bond in the substrate and form either one or two new metal ligand bonds. I think we're like the way it's depicted here is forming two, but there's also a flavor where it can just form one new metal ligand bond. For oxidative addition to be viable, I mean, again, we had previously said that for a metal to participate in pi back bonding, you need to have the electrons. Likewise, for a metal to participate in oxidative addition, it must have the electrons. So, you know, if you're taking an exam, always be wary of things, D0 metals that you know, if you're proposing them to undergo oxidative addition. Whoops. And the metal has the metal has to have a vacant coordination site for just to engage the substrate. I think that is intuitive. And then in terms of general features, because the way I've depicted this, you have electron density flowing off of the metal. The metal is getting oxidized and the organic ligand is getting reduced. This is more facile when the ligand, the metal is more electron rich. And also, because this has some parallels to sort of like a nucleophilic substitution process, it tends to be more facile when the metal involved is small. I think you know, this next point is probably self-evident, that you have an increase in the oxidation state of the metal and the coordination number of the metal. And then we'll see this play out in a couple examples, but you'll see that if you just do the formal electron counting, you'll see the d-electron count decreases upon oxidative addition. And then as a corollary to the point I made earlier, because you typically want metals, oxidative addition is more facile when the metal is more electron rich. Ligands that promote oxidative addition tend to be electron donating. So strong sigma donors, relatively weak pi acceptors, and those that have a small steric influence. So we'll talk about how ligands can be parameterized and what the key terminology and metrics are, but this would be things, for example, with a narrow cone angle, or things that have a narrow bite angle. And we'll define those terms, but just stating that for anybody who's already familiar with them. So I'll organize this section by first talking about different substrate classes that can undergo oxidative addition, and then we'll sort of unpack mechanistic features of this process and different mechanisms that can be operative. I believe in the Harvard textbook, the way this is presented is they present a substrate class, and then and then the mechanistic details of that particular substrate class are discussed. But you know, to me, I think this way of presenting it is a little bit more intuitive, so that the common features you don't have to repeat again and again. So there are three main substrate classes, and so one, and we define these. I mean, this is, to some extent, this is a little bit of a sliding scale, but we define this as when the A and B, that bond is highly polarized versus not highly polarized, and then substrates that contain multiple bonds, normally a bond between A and B remains intact. So those are the sort of three general categories. So this non-polar type, these are things that we generally would look at and we would not think like this is a good oxidant, or does not have any really highly electronegative atoms involved in this bond. So H2, like we've seen, silicon hydrogen bonds, CH bonds, SH, NH, and SS bonds. And these will generally require, so these, for oxidative addition to take place, it will generally require a vacant orbital next door to where the ligand is coordinated. And that would make sense because both of these ultimately get incorporated onto the metal. So the second type are polar reactants. And so the diagnostic feature here is that you have at least one highly electronegative atom and you would look at it and you would say, this looks like an oxidizing species. So these can be things like dihalogens, organohalides, both alkyl and aryl, as well as HX. Some textbooks will bin HX as in sort of a separate category, but you know, to me, it's more or less analogous to these others. And then here, you don't necessarily need this same requirement as above for a vacant orbital next door. And we'll discuss what I mean by that. But essentially, this process can just push electrons off of an occupied d orbital on the metal, form a new metal ligand bond, and then ionize the leaving group. Let's say B in this case, it can ionize B, and then B can eventually, in some cases, find its way back onto the metal. So when the metal is 16 electron, then both A and B ultimately are incorporated into the product of this type of oxidative addition. When the metal is 18 electron, then only one coordinates, because coordinating two would get you to a 20 electron complex. So let me kind of push arrows here. To maybe make this even more explicit. And if you're asking in this process with the 18 electron starting material, which of the two gets incorporated, it's normally the ligand that forms the strongest bond with the metal. And then the last type are so-called intact reactants. We've already seen this actually in a couple of the practice problems we've done. So we talked about O2 and how it can coordinate in this bent fashion and even bridge multiple metals. And then we talked very briefly about this alternative process where O2 can coordinate in the side-on fashion, actually oxidize the metal and then remain as a ligand on the metal. So that looks like this, and then we saw a problem where we had reversible oxidative addition to an alkyne to make a metallocyclopropene.
Are we going to say that the polar or the non-polar substrate classes are better at oxidative addition, or is it system dependent?
Let's come back to that question. I think there's some system dependence. Let's talk about some of the underlying mechanisms by which oxidative addition can happen, and then if it's still unclear, we can come back to that. But Camille, I would say as a first pass approximation, like things that are more oxidizing in general are going to be better for oxidative addition. So I think if you had to make a categorical statement, you'd probably say that polar are generally better in oxidative addition just because they're more oxidizing, if that makes sense.
Sounds good.
And then this we alluded to very quickly at the end of last class. Sorry to run through that. Is, you know, the vast majority of what we'll cover in class are these monometallic processes, but I always try to give a flavor for just that there's more in organometallic chemistry than meets the eye, as I'm constantly reminded. And so there are multi-metallic oxidative addition processes. And I think I think the key thing to remember here is now the oxidation state. Oxidative addition in general oxidizes the metal from, you know, N to N+2. When you have a multi-metallic system, the metals can share the oxidation state adjustment. And so I'm drawing this one here as a homobimetallic, but you could also draw it as heterobimetallic. And by strategically, so we'll see this, I'll just provide one brief example and then we'll come back to this phenomenon in one of our later problems of the day today. Just by taking advantage of the unique mechanistic features of these multi-metallic oxidative additions, you can also do some fundamentally interesting and enabling chemistry. So I always have so many windows open on my computer. This is
Hey, Kiri.
Yes.
Quick question for that last example. Is that like a radical one electron from each metal, or is it still 2 electron from one of them and then the other metal will transfer an electron to the metal?
Yeah, I mean, in this, how I have it defined it here, there's no mechanistic connotation. I think in principle it can be either, but it's certainly not restricted to a radical based process, if that makes sense.
All right, thank you.
Yeah, so here's an example from our chemist of the day from last time, where the overall transformation, I'll get the reference. Probably looks familiar. It's a Hartwig, Miura, Ishiyama type borylation, CH borylation reaction. But the cool thing is that by using heterobimetallic catalyst in this case, containing a copper iron bond with a NHC ligand, and the ligand here is Iper, which is just, and we'll cover this later, so if this is confusing, don't worry. and this is what Tim was alluding to, is does this process have to be 2 electron, or can it be 1 electron? And the key step here is this bimetallic mediated HB pin cleavage step. So I understand this is you know, fairly complex as examples go, but I do want to give a flavor for what we mean when we say these multimetallic versus monometallic systems. Any quick questions on that? Otherwise, we can press forward. Okay, so now let's go through oxidative addition can take place. And so one that's common for these nonpolar substrates is a so-called concerted pathway. And this is, the mechanism is exactly as it sounds. Concomitant formation of both the metal A and the metal B bonds with oxidation state increase at the metal. This transition state here is a 3-center 2-electron, where you have a side-on approach of the sigma bond that ultimately is cleaved. The reaction is stereospecific by virtue of having a stereochemical outcome that's encoded by the underlying mechanism. And then if you're talking about stereochemistry at A and B, let's say that the bond that's being added is carbon containing and it has a stereocenter, it is stereoretentive. And this contrasts the other pathways that we'll cover. As we covered before, we need a coordinatively unsaturated metal. In terms of underlying kinetics, usually this process is second order, because the part that's slow is the bimolecular association. And then in contrast to what we'll see next, where you have substantial charge buildup during the transition state, you see that in this concerted pathway, there is not much charge buildup in the transition state. So if you're running, say, mechanistic experiments, and the rate is not particularly sensitive to solvent dielectric constant, that might be an indication that you're in a concerted pathway, because in a polar pathway or a nucleophilic pathway, you'd expect substantial charge buildup during the transition state.
I have a quick question.
Sure.
So you mentioned it's a 3-center 2-electron transition state. Wouldn't it be a 3-center 4-electron, considering that also the sigma bond of the AB system is involved in this?
Let me see. Yeah, I might have miswritten this. TAs, is that right? 3-center, it should be 3-center 4-electron.
Yeah, I guess the definition for 3-center 2-electron is that 3 atoms would be sharing the 2 electrons, and like through a combination of 3 atomic orbitals. So
So what's the
should be
verdict?
fine, right? No, I think what you wrote should be fine.
Okay. I think it depends on your definition here.
It's still two
You are right.
electrons.
I think we're talking about the same thing, but using different terminology.
Okay, thanks.
Yeah. Okay, so let's use look at a specific example here that's related to what we've already covered. So let's just take a look at the sort of simplified MO diagram for H2. So we said these so-called sigma complexes, the filled sigma bond of H2 serves as the sigma donor to the metal, and then a filled d orbital on the metal can back donate. I'll do these different colors just to make this as clear as possible. So you have a filled d orbital from the metal, now filling the sigma star antibonding orbital. We showed before that in these sigma complexes, this bond weakening is clearly evident from the crystal structures. Just as a reminder of numbers that I think I jotted down before. And then when taken to the extreme, this leads to sigma bond cleavage. And actually, in many cases, this process is so this is really the kind of just the underlying mechanism of how H2 can be cleaved. And in many cases, this can be a reversible process. And there are some interesting underlying mechanistic experiments that can be done, like you can follow the H2 adduct, the sigma complex, has a different proton NMR spectrum, for example, than the dihydride species. And that can be followed by NMR, and you can look at temperature sensitivity of the speciation, for example. Okay, now the nucleophilic pathway. Let me draw out the transition state to illustrate this point I made earlier about partial charge buildup. So this pathway is more common for polar substrates. Specifically where A or B is polar. And the group that's ultimately lost is a good leaving group. It resembles a SN2 mechanism And then hopefully you have an appreciation for the fact that, like an SN2 mechanism, it would be, if A is a stereogenic fragment, it would be stereoinvertive at A. One of the diagnostic features in terms of product outcome is if you see overall transition. So you have, say, D8 square planar, and the product has the A and the B groups added in trans orientation to now it's octahedral. That would be an indication that it was a nucleophilic mechanism.
In what you drew, would it make more sense to have the delta plus on the A and not on the metal?
Sorry, who asked the question?
Camille.
Oh, hi, hey, Camille, thanks. Well, I guess you can make the argument either way. There is some positive charge buildup on the A, I guess, but because the metal is overall oxidized to +2, there's, I guess, I would define most of the charge buildup in that transition state as being on the metal.
Yeah, Camille, and particularly if you look at like M and B are not defined here, but B may be a halide. So typically when you compare M and B, the halide would is much happier taking the partial negative charge than relative
But
to the metal.
I think Camille's asking about, like in the example you gave, say it's like a aryl halide, how much partial positive is there on the carbon of the aryl versus on the metal? It might depend a little bit on the specific case, but I think in general most of the charge is built up on the metal. So the rates of a nucleophilic pathway are sensitive to the ligand environment around the metal in predictable ways, and the general trend here is that more electron donating, more sigma donating ligands will lead to faster oxidative addition, all other things held equally. So the specific example here I have is a series of mostly tetra, but in some cases tri or di substituted coordinate nickel 0 complexes. Now, for a tetra substituted nickel 0 complex, it certainly needs to dissociate one or maybe even two of its phosphine ligands to allow free coordination sites for oxidative addition. But again, this is about the best you can do for sort of a homologous series. So in this series, trialkyl phosphines are most reactive, then triaryl phosphines. Then if you replace one of the alkyls with an alkene, which is pi accepting, that's a little bit less reactive. And then nickel cod, where you have only alkene ligands, probably you'd lose one cod, and then that would be the form that's the reactive for oxidative addition. Let me draw out cod in case. So just cyclooctadiene. Then you have a lot of pi accepting character, and so that's going to be the least reactive. So better leaving groups lead to faster rate. Again, just in direct analogy here to SN2 chemistry. So this is the order. And then also in a direct analogy to SN2 chemistry, more hindered carbogenic fragments are less reactive or slower to react. I'll leave this in case anybody is jotting down notes. Okay, let's consider now a case study where we're trying to disambiguate between concerted and nucleophilic pathways. And to do that, we'll consider this complex. Does anybody recognize this complex and want to provide the name?
Is this Wilkinson's?
No, that's iridium.
This is an iridium complex.
So that's a VASA complex.
Vasquez complex. Good. Thank you. Is that Win? Thank you, Win. And Tim, maybe I'll continue to torture you. How about electron count for this complex?
So 3L ligands, 1X ligands. I gotta look at iridium in a second. 16.
Okay, so you said 1X type, so iridium plus 1, D8. D8, iridium is 0 is D9, so D8, and then you said 16 electron complex. And this makes sense, D8, square planar. Okay, good. Anybody got anything different? And one of the power, maybe I'll just a very brief tangent. I think the part of the power of Vasquez complex for when it was developed in the early 1900s is that it undergoes a remarkably broad range of oxidative addition processes, including processes that involve mechanistically distinct steps. And it has this convenient carbonyl that is an IR handle for monitoring reaction progress. So in the early mid 1900s, when people were interested in what's going on mechanistically in organometallic chemistry, but NMR was not the powerful tool that it is now, this was an incredibly powerful platform for studying reaction mechanism. It's interesting because in and of itself, it's not like one of your most reactive complex catalysts for, let's say, hydrogenation or other useful reactions, but its utility really comes in facilitating so much mechanistic work over the years. Okay, so let's first consider oxidative addition with H2. We said this is a non-polar substrate type. So what would we expect to happen here? Let's see, Taiwei, are you on? Aaron, are you on?
Yes.
Oh, Taiwei's on, okay. Hi, Taiwei. What's the product going to be?
Oh, let me see.
What do we think here? I guess from above, we know it's going to be a dihydride adduct. So where will the
I
hydride
think it
ligands
should
be?
be sixth position, and but yeah, it should be sixth position.
Okay.
And form a octahedral complex.
Okay, very good. And now electron count very quickly for this.
And for the second one, it should be nucleophilic.
Okay.
And the iridium, the iodide, the methyl iodide would attack the iridium, Yeah.
Okay. Plus.
And the iodide anion would attack the metal center.
Okay. And they're going to be what orientation?
I think it should be
Stereochemistry.
trans because
Okay.
the first step, it will not change the configuration.
Okay. And then very quickly, the oxidation state and the electron count for these two, and overall electron count.
It should be iridium +3 and
Okay.
What's that? 18 electron.
Okay, and so iridium +3 should be D6.
Should be, yeah, D6.
And then 18 electron complex. You have D6 plus 6 ligands. Okay, and then I think we could, just to save time, we'll say this is the same for the. So I think partly why I take the time to ask for the electron counts is just to illustrate the points that we made earlier about how this affects the d-electron count and coordination number. And I guess we can also just say coordination number 4 in these cases and coordination number 6 in this case. Okay, thank you, Taiwei.
Hey, Kiri.
Any questions on that? Yeah.
For the top case, is for the chloride going down to the bottom coordination site, does it actually depart, or is there some sort of concerted rearrangement of that ligand?
It departs. So it's lost as iodide and then it finds its way back home.
Oh, for the top one. Oh, or the chloride departs and then rejoins the complex.
Oh, sorry. I understand your question. So in this case, the chloride does not depart. So you're asking about how the chloride gets from an equatorial position to an axial position. Is that what you're asking?
Yeah.
I think it will stay on the metal while it's doing this.
Okay.
It just distorts its geometry.
I see.
Kiri, just continued with Carter's question. Why is the chloride going down instead of the carbonyl or the triphenylphosphine group? Is that the chloride favor cis effect or something like that?
Yeah, I mean, I think I guess what I can say is this is the experimental outcome. And so you, let's say you were taking a test and you put one of the others going to that position, you might not, it might not be obvious ahead of time, but I think one of the, general features is that, it will try to get to a thermodynamic minimum where you have the weakest trans effect ligands trans to the strongest trans effect ligands. And you can maybe do this thought experiment of swapping all of these in for each other and see if you can convince yourself that this is a low energy compared to others that you might get.
Okay, thank you very much.
Yeah.
In this case, also, if you look at the transition state for these, one of these ligands will have to get pushed down. And if you draw the filled orbitals and you want to maximize pi back bonding, you would want to do that to the CO and the triphenylphosphines. And this pi back bonding will be weakened as you push them down into the axial position, whereas they're maximally strong in this equatorial. So in this case, the chloride is the easiest to push down because there's minimal pi back bonding. So it's sort of the most stable thing to shove down into that axial position. When you have these specific ligands, like Kiri said, the situation can get very complicated if you don't have things that are clearly strong pi accepting ligands and something that's not pi accepting at all.
Yeah, thanks, Tanner. And then maybe just to continue that, in this case also phosphine, bulky phosphines generally are going to want to not be cis to one another in an octahedral complex if they can avoid it as well. So Tanner mentioned the electronic component, and there's also a steric component. but yeah, it's great question. Good eye for detail there. Okay, let's go now to the last, I guess, sort of canonical type of oxidative addition, and then we'll talk about a special class that we've been here, but is not strictly an oxidative addition. So the radical pathways, Tim was alluding to this as well in an earlier question. So what we've discussed up until this point are processes that proceed through closed shell intermediates, but they can also, oxidative addition can also take place through open shell intermediates, and this is especially common for first row metals. Not unique to first row metals, but especially common for first row metals undergoing oxidative addition. There are two flavors of radical oxidative addition, a so-called chain type pathway and a non-chain pathway, and the differences, underlying mechanistic differences are sort of depicted in general terms and these summary schemes. So if we want to push, I don't know, do I dare try to push arrows? I'll probably screw something up. So in that non-chain pathway, you can view this as a electron from the metal, from a filled d orbital on the metal, is effectively engaging an SET transfer to homolyze, let's say the organohalide or whatever else this would be, and then you get recombination of the carbon-centered radical that is thus generated. Well, I realize I drew these arrows in not the right way. Sorry if that's confusing. And then recombination of the thus generated radical. And then the chain pathway where you have a propagating carbon-centered radical that can form first a bonding interaction with the metal, and then this species, which is now open shell, can induce homolysis of the metal halogen bond, ultimately getting to the same product and also the same type of product as what's shown above. Radical-based processes can happen for both polar and non-polar reactants. A distinguishing feature here in terms of underlying mechanism is that the carbogenic group will undergo racemization. And the reactivity here is a departure from what we saw before, but very much in line with what we've already learned in other classes about radical processes. So it's faster. The rate hinges intimately on the stability of the carbon-centered radical that is generated, and the order is tertiary, as radicals are more stable than secondary, are more stable than primary, are more stable than methyl. And so let's consider quickly one case study. So I said this process is common for first row metals, and then the example I'm going to show you is not a first row metal example. So here we have a platinum 0-tris phosphine complex. Which is very electron rich and can homolyze this organohalide. Radical recombination in this case is fast. So the reaction is second order in platinum and in organohalide. And here's an example of the substrates that are used, and I'll let you think on your own about, based on the fact that I'm telling you it's a radical mechanism, which of these you'd expect to react faster or slower. Okay, so let's just quickly go through this next section, and then we can dig into this a little bit more detail with problem of the day number 1. So the last process I'll cover is called oxidative cyclometallation. I guess it's debatable whether this is a true oxidative addition or not, but I just bin it here because there's not really another convenient place to talk about it. And this is a process where you have 2 pi systems in a metal that can engage in a cyclization process that, like oxidative addition, increases the oxidation of the metal by 2. It's more complexity generating in the sense that it creates 3 new sigma bonds, 1 between the 2 organic fragments and then 2 between the organic fragment and the metal. And this is a constituent step of catalytic processes we'll see down the road, including alkene and alkyne trimerization and the venerable Pausen-Kahn reaction. So it shares enough similarities with traditional oxidative addition that we cover it here. Okay, let's jump into problem of the day number 1. Are you able to see this? No. Okay. How about now? Okay, so this example asks us to consider a nickel catalyzed cross-coupling reaction. Can be considered a Stille nickel catalyzed alkyl Stille coupling. And we'll cover this in more detail later, but the constituent steps involved are, in some order, oxidative addition, transmetallation, reductive elimination. And specifically, it's asking to consider only the oxidative addition step and just ask, how is that happening mechanistically? And how would you design an experiment to rule out other possibilities? So think about all possibilities. I mean, we just covered the key types, so it's sort of self-evident what we're talking about, and then design an experiment that would allow you to rule out the other possibilities. So we'll give this just a minute, and then I'll call on a volunteer. Okay, what do we have here? How about Win? What's your idea? Or what are your thoughts?
So, I mean, there are just 3 possible mechanisms.
Yeah.
You just showed so far the concentric one, the polar mechanism, and the radical.
Yeah, okay. So how would you disambiguate?
For radical mechanism, I mean, the fastest way is to have some source of radical scavenger or a radical clock to see if it affects in the reaction.
Okay. So what kind of radical scavenger would you think about?
I'm a little bit hesitate to propose tempo because tempo is also an oxidant that may shut down the reaction in different way. But yeah, I mean, that's the fastest one to think. The other possibility, I think, is trinitrotoluene, I believe. Is it?
Trinitrotoluene?
I mean, it definitely is some polynitro aromatic compound, but I can't remember. But it is some. It's also a radical scavenger.
Okay. One I think that's of this general flavor that you're thinking about is.
Oh yeah, right. The
BHT. I can't remember this. Butylated hydroxytoluene, BHT. So yeah, I think. And then the other thing you talked about was radical clock. So let's unpack both of these quickly. So these radical scavengers, I think you have to be cautious for the reasons you mentioned, because let's say tempo is also an oxidant and can affect the metal in more significant ways than just trapping the radical that you're hoping to generate. But it is commonly used, and I think one way that you can get more insight is if you're able to trap the alkyl tempo adduct and characterize that by NMR or mass spec or a number of techniques, then that is pretty good evidence that a radical is generated, alkyl radical is generated under the reaction conditions. And then what were you thinking about for radical clock? What type of radical clock?
If we have a the functional handle, let's say a cyclopropane substrate.
Okay.
Yeah, and to see if, this radical clock is usually fast, so like unless the reaction is super fast, beyond the radical clock, then we should observe some of the radical clock reaction.
Okay, do you happen to know the rate of this radical clock opening?
I can't remember, but that thing should be 10 to the power of 5 or something.
This one is first order rate constant of 10 to the 7.
Okay.
And then the other, I think maybe what you're thinking about is the other type of radical clock that people like to use. 1, 2, 3, 4, 5. Is this 5XO cyclization clock, and I think this one has a rate constant of about 10 to the 5th per second. Now, one of the caveats here too is that you have to be a little careful, because metals can open these same radical clocks by closed shell organometallic pathways, by beta carbon elimination or cyclization.
Yeah, right.
So it is commonly used, but there are some caveats. Okay, anyone else want to volunteer another thought? Thanks, Wynn.
You can do kinetic studies.
Okay, what would you expect to see from the kinetics?
So
Alex?
Well, I guess one of the, for looking for concerted, you can think about changing the polarity of solvent that you're in and seeing if you have any change in the kinetics of the reaction. And if you don't, that's evidence for a concerted reaction.
Okay, super. Any other thoughts?
I was thinking you could somehow make the substrate stereo defined either through deuteration. Then you could see if it's stereo retentive or stereo invertive.
Love it, Daniel. Okay, so make this stereochemically defined, or enantiopure, enantioenriched at least, secondary alkyl halide starting material, subject it to the reaction, and see if you see an enantioenriched product or a racemic product.
Hey, Kiri.
Yep.
Is there not the possibility for an SN1 type pathway for the nucleophilic mechanism? I guess, I mean, you know,
Yeah,
for some
it's a good thought. I mean, in principle, yes, I think that you could rule out through other well, maybe let me backpedal on that. I think in general, radical would be much more likely than an SN1 type pathway where you have heterolytic cleavage. I mean, where you like have a well-defined carbocation in the intermediate in the reaction solution in the presence of the metal. I think that's not going to be the lowest energy pathway typically, which is not to say it would never be the case, but I think it's not likely. So Daniel's question, just to come back to Daniel's question, or Daniel's suggestion, which was a good one, make it an enantio-pure starting material and ask whether the product is enantio-enriched or racemic. That's a common technique in this area. Now, one of the challenges is sometimes these enantiomerically enriched secondary alkyl halides are like so hard to make in high enantiopurity that people don't want to do that. And so along these same lines, another trick that people like to do is to take a norbornene where the halide is up or down, and if these converge to the same diastereomeric ratio, product ratio, then that would be evidence of a common intermediate, and that common intermediate is likely to be a radical. Okay, and this is a reference we'll send out in case anyone wants to take a look in advance. This is a paper from Greg Fu's lab, and you can take a look at what they.
Could you also use, oh, sorry.
No, go ahead, Daniel.
Could you also use different alkyl halides? See how the rates change as well? I guess that's maybe another.
Yeah, definitely.
Approach.
Yeah. Yeah, this goes, maybe I might not have even noted this. So if I, yeah, that's a good reminder that I forgot to note this. In the radical section. But you could consider changing both the leaving group or the carbogenic group and look at reactivity trends, and that would give you some indication. I think one of the defining features is that in a nucleophilic pathway, the tosal is a good leaving group and highly reactive, but in radical pathway, those typically are not good substrates. So those can be good mechanistic probes. Okay, let me just take the remaining time we have and cover some of the quick talking points about reductive elimination. This I'll go through relatively quickly, in part because reductive elimination, by definition, is the microscopic reverse of oxidative addition. So a lot of the trends that we'll see are just the trends we've covered in reverse. And so in a reductive elimination event, the coordination number decreases by 2, the oxidation state decreases by 2, total electron count decreases by 2, again, everything moving in the opposite direction, and the d-electron count increases by 2, because now you're in effect pulling electrons off the metal back, off the ligands back onto the metal. At least for a concerted pathway, we can talk about the fact that, there's a concerted pathway, and then there are also nucleophilic SN2 type pathways. But in general, the concerted is the most common, and for a concerted pathway to take place, the ligands involved in the reductive elimination must be cissoid. And so that's illustrated by this dihydride example, where the one on the right undergoes rapid H2 reductive elimination, whereas the one on the left is actually relatively stable. It does not eliminate H2. And again, counter to what we saw in the case of oxidative addition, now reductive elimination is promoted by low electron density on the metal, sterically demanding ligands that you can think of this as squeezing out the group that gets reductively eliminated. Again, parameters here like cone angle, wide cone angle, bite angle, wide bite angle. And then a key trend is that groups that have higher S characters, so things that are SP or SP2 hybridized, tend to be easier to reductively eliminate. And this, I think, is one of the underlying reasons why, just, you'll read statements in the literature like SP3 cross-coupling is hard, SP2 is now well developed. SP2 couplings in general are easier because the reductive elimination step is easier, because the groups that are being squeezed out have higher S character, meaning that the orbitals involved are more spherical, which means they're easier. It's easier to touch two spherical orbitals together. If you consider my hands and they're two beach balls, I only have to move them like this and they'll be touching. If they're like pool noodles, like P orbitals with a lot of P character, then I have to move them all the way like this to get the ends to touch. I can't tell if Anne likes my analogy or not. She's grimacing at me.
I was trying really hard not to laugh.
Yeah, you guys can laugh. I work on these analogies to try to bring a smile to your face. And then, as often the two groups involved in reductive elimination are not the same. I mean, in this case we saw before H2, they are the same, but often they're not the same. And in practice, the transition state thus has an inequivalent charge distribution, and in practice, one of the groups ends up functioning as a nucleophile, and one ends up serving as the electrophile. So this makes it sometimes a little complicated. Like if you have a metal aryl, it's not always the case that an electron withdrawing group accelerates reductive elimination, an electron donating group retards reductive elimination. It depends whether that group is participating in effect as the nucleophile or as the electrophile. So this is a caveat you have to think about when you're doing mechanistic studies. Historically, it has been difficult, and now there have been great advances in the last 2 decades or so to reductively eliminate carbon heteroatom bonds. This is for a number of reasons. I'll give you two to kind of chew on, two rationales for why this is hard. One is that in general, nitrogen, oxygen, and fluorine are highly electronegative and relatively non-polarizable. They're small groups. They don't have a lot of electron density. And so to the extent that reductive elimination is bringing two groups together, when you have something really, really small, it's hard to bring it into contact with another group. And then there's this other element where when you're doing reductive elimination from a 3-coordinate intermediate, which we can talk about in more detail in next class, is that these proceed through typically a Y-shaped intermediate, because not all 3 ligands are identical. There's some distortion. And the small group, the electronegative group, actually wants to be at the end of the Y, not the V part of the Y. So that's exactly where you don't want it to be. And this is the origin, like historically, when people were trying to do CF reductive elimination from palladium-2 centers, instead they would get C phosphorus reductive elimination to make a phosphonium, because the fluoride actually wants to be at the exact opposite end of the transition state. And this is, again, I'll let you think about this on your own, but this is because if you think about how charge is distributed in this transition state, the most electronegative group, I think, wants to be farthest away from the bonds being formed. Okay, I'm already a couple minutes over. As I said, in this 3-part lecture, we have some flexibility. And it's sort of fluid in terms of what's covered each day. So we can wrap things up here. Oh no, maybe you can indulge me for another 2 minutes so that we can do our poll. I don't want Van to have set up the poll and not use it. So we can quickly do this poll, and then I'll let you, and then we'll just chat very briefly about it, and then we can hit the rest part of this problem of the day at the next class. Okay, so you have this poll, and the poll is to ask in our problem of the day, which of the two, let me pull this up. Whether A or B is going to undergo reductive elimination faster. Hopefully everyone can see this. Oh, there's a typo. There should be PH2. Sorry about that. Is everyone able to see these two structures, or you have them on your computer? Okay, we're polling neck and neck right now. Okay, now one is pulling into the lead. Okay, give it another 5 seconds, man, and then you can kill it. Okay, in the end, we got most people the correct answer. Eleanor, what did you answer and why?
I answered B, but I don't think that's right. I just thought it looked like the ligands were bulkier, so maybe it would force out the.
Okay, and what would be the other argument?
I'm not really sure. Sorry.
Okay, anybody want to volunteer quickly?
I said A because the ligands are cis to each other.
Perfect. Thanks, Alex. Yeah, you have this interesting case where, as Eleanor said, the one on the right actually intuitively looks like a bulkier ligand. It has a wider bite angle. It's actually the subtype we can talk about called trans-spanning. But by virtue of being trans-spanning, it means that the two methyls are actually on the opposite ends. They're trans to one another in the complex, and they need to be cis-oid to reductively eliminate. So that complex on the right turns out to actually be thermally stable, even in polar solvent, even at high temperature. It's an example from the group of Stille. Whereas on the right, the one on the left is more hot to trot in terms of reductive elimination. So with that, now I will give you these last two to think about in the next 2 days, and then we can talk about them at the beginning of Thursday's class, which is with now that you know which is more faster to undergo reductive elimination and that B doesn't, how could you how can you understand this experiment, which is you add methyl iodide and now it extrudes ethane very rapidly, even at room temperature. So what's going on, and then how would we interrogate that? Okay, I will wrap things up here. Sorry for going over time, and have a good day, everybody.